Okay, guys, welcome to the second session of the ML course. Today, can you guys tell me if you can hear me first? I'd just like to know that. Yeah, in the chat, simple yes will do. Okay, cool. Fine. So let's begin today's session. I'm Shreyas, and I'll be taking today's session on logistic regression and K-means clustering. So we have two more mentors in the chat. So if by chance I'm not able to take your queries, then they will definitely get back to you on the chat. So let's begin. So here is a little recap of what happened in the last session. That was linear regression. So this is the data set which we given. Let's say this left image you can see here, and we have a bunch of data points. And assuming, let's say this is the house price prediction, and we want to, given the x values, it can be anything. Let's say for this sake it's the size of the house, and our y values would be the price of the house. So we want to fit a best line through this data in order to predict, say, another point which we don't have any data for. So that's what linear regression will help us do. So we defined the loss function here. J of theta is 1/2m summation of h of x minus pi whole square. So this was commonly known as mean squared error, right? So you also have different loss functions as well. People are asking. You have mean absolute error, and many more. The reason we would usually choose this over the others is because differentiating it would make it much easier. So this is your update statement over here, the second line. So this is gradient descent, right, which I think all of you are clear about from last session. So this is where each parameter you would update it using the learning rate alpha followed by the differential of your loss function. Sorry. So one thing you need to notice is the simultaneous updates, right? So you want to use the same theta values for all your updates that you had used for your previous iteration. So this is the formula which we had used for multiple linear regression. I'm sure you all remember this. So you have h of x equal to theta naught x naught plus theta 1 x1 and so on. So you have x naught, x1, x2 all the way till xm to be your features, and theta naught all the way to theta m are your weights or your parameters. So did anyone after the last session sort of go and try coding linear regression on your own? Anyone? Okay, fine. So this is just a little side note on how things are sort of stored when you're trying to implement such algorithms in code. So we know that your X matrix is represented like this, where each row is one house, right? So it's assuming we're taking the house price analogy here, each row will be one house. So x naught of 1 would represent the first feature of your first house, x1 of 1 would represent the first feature of your first house, all the way till xm of 1, right? And this goes on for n houses which each have m features. So this is your n cross m matrix. And assuming, so this I think is already known to you. One more thing is your theta matrix. So this is basically all your weights or your parameters. So they'll be stored like a vector form like this. So you'll have a column, either a column vector or a row vector. So depending on implementation, you'll have different representations. So do you guys know what I can do using these two matrices? Can I get this equation above? Any guesses?
Multiply.
Yeah, correct. So which one would I multiply first? Is it x times theta or theta times x?
X times theta.
X theta.
Yeah, perfect. So if I do that, you can see that I'm going to get the same equation above for each house. So I'm going to have n number of houses, and then all of these are added up, and you'll get your predicted value for your given model. So this is much, so whenever, maybe if you're reading papers or something, they're most likely going to use this representation here, that is matrix representation, rather than this one over here, because it becomes cumbersome to write this down every time. So also one thing to note, sometimes you might find them using theta transpose times x. That is because your x matrix, since here we're representing it row wise, that is each house is stored row wise, they will be storing it column wise instead. So in that case, it's the same representation, except that it will be theta transpose times x to get the same matrix over here. Right? Any doubts in this? Okay. So yeah, if you guys don't know matrix multiplication, it's better to go and just refresh on, because it is pretty important. You will find a lot of these linear algebra things happening in a machine. Okay, so we'll get started with logistic regression. So before I tell you what it is, let's understand why we need it. So let's say I have a model and I'll give it an email and I want it to predict whether it's spam or not. It's basically a spam filter. So linear regression would predict continuous values, right? Basically it's a straight line. So it's going to be predicting continuous values. But do you think I can use continuous values to predict spam or not spam, if there is a way to do it?
Maybe like everything above the line would be spam, everything below the line would be spam.
You could do that. The thing is, that is only helpful if your line is a horizontal line, right? Suppose if, so because if it's a straight line and we have certain value of x, like I showed here, over here, so if a certain value of x is always going to predict a certain value of y, it's not particularly useful when it comes to classification as such. So it's all right, but then we have a certain transformation which we would apply, and I'll tell you that how it works. So you guys understand why we can't use linear regression for this, right? Because linear regression is always going to predict continuous values, as opposed to we want certain discrete values here. Suppose for spam, the way we would predict it is the model will predict the number 0, and because it's 0, we will infer from that it's not spam. And if the email is spam, then it will predict 1. So in this spam filter, it's called binary classification. So what that means is that there are only 2 classes and you predict either one of them. So because it's binary classification, your model is only going to predict 2 numbers, that is either 0 or 1. There are no continuous values predictions happening over here, right? So let's say that I'll try writing. I'm not great with it. I'm using the mouse right now. So just bear with me. Let's say my data set is something like this, right? Over here, and a few points over here, like this. Now, if I use linear regression on this data set, what line do you think it's going to predict? Any guesses?
A horizontal line?
Okay. So one might say it might be like this. One also might say it could be like this, right? So either way, do you guys agree that is this a good representation of our model? Like, do you think it fits the data well?
Nope.
Oh.
No. Okay. So let's say I want to do something to this line itself, right? I want to transform this line such that it fits this data much more better. So now, can you guys tell me what the range of values that I get from a straight line? What values do I get from it? Like the range?
You're only getting 2 values, right? 0 or 1?
No, that's for logistic regression. I meant linear regression. So suppose this straight line here. What are the range of values can I get from it? What is the range of a straight line, basically?
Minus infinity to
Yeah, infinity basically.
Yeah. So all real numbers, right? Minus infinity to plus infinity. Now, for this classification problem, I only want two numbers, 0 and 1. Now, let's say that, let's go a little step down from that. I want values from 0 to 1, continuous values. So do you know any transformation or any function that takes in real values and it outputs values from 0 to 1? Do you know any function?
Step function.
The step function, does it give only values from 0 to 1 is my question. Suppose if I
Wait, fractional part. Wait.
the fractional part would look something like this, right?
Yeah.
Yeah. Okay, fine. So this is fine. I mean, this makes sense. But let's say something that would fit this data also. I have two concepts.
It's like a sigmoid function with an absolute value, so it doesn't give -1. That's all.
Yeah, okay. Cool. So sigmoid function. I don't know if how many of you know about this, but it's going to look something like this, the sigmoid function, right? So the sigmoid function will map all your real numbers to the set of 0 to 1. And that's basically what we want. Now, the fractional part thing also makes sense, but then we want it to fit this data as well, right? Which is why we're using sigmoid right now. So, like this. So linear regression will do something like this to your data, and logistic regression would transform this line basically using the sigmoid function. I'll explain that in a while, and it'll give you this line. Now you guys will agree that this is a much better representation, right? It's going to fit the data much better. So let's see what that is. So logistic regression, now I'll define what it is. So initially your first step is the same as linear regression. So basically this is where that matrix multiplication happens, right? The one I explained to you in the previous slide. You would have your weights or theta parameters and have your features, and you multiply them all and you add them up together and you get a net input here, right? And that is basically, so if it's a straight line, then we're dealing with only one feature and two weights, but usually you would have also multiple weights and features as well. So just to make it easier to draw, I used only two, I draw a straight line, but you can also think of this as different in other dimensions as well. So you get this, you sum all of them up and you get your net input, right? And that is the straight line which you get. Now you're going to apply the sigmoid function or an activation function, right, to this line, which is going to give you values from 0 to 1. Now once that's done, this is where the classification happens. You're going to apply a step function, and I'll explain what that is in a while. But this is basically your entire pipeline or schematic for logistic regression. Okay, so any doubts, or is everything's clear so far?
But when you're taking 0 and 1, isn't that only for a binary classification?
Yeah, as I explained. So this is basically for binary classification only, where you would only have zeros and ones. Now, if you had more classes, again, suppose if you had attended the orientation, I think you would have seen the dog breed classifier. So you have like a bunch of breeds, like 150 or something. So that's where you have 150 classes. So that's where you would use different classification algorithms. Logistic regression wouldn't make sense there because this is only for binary classification. If it was for more classes, you would use, so you'd have decision trees, which is being taught in your next session. And you'll also use neural networks, which, if I'm not wrong, I think would have been started in your deep learning sessions as well. So is there any doubts so far?
So logistic regression is only applied on binary classifications.
Usually, yeah, this is what you use for binary classification. Sometimes in neural networks, you'll also use this as activation functions as well. You'll understand that later when deep learning sessions begin. But usually this is what happens. It's basically the transformation to make it from 0 to 1.
Cool.
Okay.
Can you show the first slide one sec?
The first slide?
Yeah.
This one?
Oh, okay, cool.
Okay. Fine. So the sigmoid function, so this is basically the expression for it. It's 1 by 1 plus e power minus x. So what this does, I'm sure you can apply your limits and like figure it out. So if z is approaching negative infinity, right? So then this will become, any guesses?
One.
No, this will be negative of minus infinity, right? So it's looking e power
Oh,
infinity.
sorry, yeah, 0, 0.
Yeah, so this will become 1 by infinity, which is 0. So that's basically given by the curve here. And at positive infinity, this will become 0 and this will become 1. So it approaches 1 at positive infinity and 0 at negative infinity. And at 0, it's going to approach half, 0.5. So that's given by this curve over here. And okay, so this theta transpose x, that's what I told you in the first, I think the second slide. This is where your x matrix is represented column wise. That's why you get this expression. But it depends on how you define your x matrices. So if the way I represent it, then you would write g of x times theta instead of this here. So just to let you know. Any doubts so far? Okay, fine. So moving ahead, so the loss function for this. So the loss function which we used for linear regression was your mean squared error. Do you guys think we can use the same loss function in this case as well? If yes, why? And if no, why?
We can't exactly, because the values are not linearly, like when you find the difference, it's a linear thing, but it's not a linear graph. So to see if it's correct or not, you can't exactly tell it.
Yeah, okay, that's fine. So basically, since you don't have continuous values, to find the difference would make no sense here. So in this case, you would have to make it sort of specific to the classes which you have. So let's say for y equal to 1, that means that the email which we've given to you is a spam, right? And this is your graph here, and h of x is varying from, let's say, 0 to 1 over here. And you have your loss from minus 1 to 1. We'll figure that out. So let's say, so now let's say that the email I gave you is spam, and my model predicts it to be not spam over here. What should my loss be? Should it be high or should it be low?
High.
Hi.
Yeah, correct. So ideally it will be somewhere near infinity. So I'll just make a point over here. And let's say that given it's spam and my model predicts it to be correctly spam as well, what should my loss be?
0.
Yeah, so over here. So basically you're going to get a curve like this by your loss function. This is only when you have your y to be equal to 1. That is, your email is spam, right? So let's take this case where your email is not spam and your model predicts it to be spam. How much should my loss be, high or low?
Hi.
Okay, fine. So it'll be somewhere over here. And if given my email is not spam and my model predicts it to be correct, not spam, should my loss be high or low again?
Low. Low.
Yeah. Wait, what? I didn't get you.
Low. 0.
Yeah, 0. Yeah,
0.
so it's going to be over here, right? So I'll join these two again like a curve, right? So these two are my loss curves or loss functions, and you realize that I have two different loss functions depending on my class. So let's see, do you guys know the name for this graph? I'll just give you a hint. This is minus log x, okay? So this is minus log x. So so if you know this minus log x, can you guys tell me what this graph might be? Using your graph transformations which you learned.
T to the power.
I'm sorry? Use the log function as your base and then transform that into this. Any ideas what it could be?
E power x?
It's e to the power minus x.
Oh, e power
E
plus.
power minus x or e power x would be something like this, right? Over here. At 0 it will be 1. I'm sorry, over here.
Oh, yeah.
Use a log function, right? And
Okay.
transform that into this. To this. It's based on log itself. Okay, can you guys just try it out and tell me what it is?
You can subtract 1 from the y and add 1 to the x, right? On the graph that you just made.
You could. I'm not sure whether these curves would coincide. That's the only issue.
Oh,
Yeah, I mean they would make sense in these endpoints, yeah, for sure. But in terms of the curvature and all, I'm not really sure if it would make sense. I'll just try with log and see, and try it out. Okay, let's give you another minute and then I'll tell you what it is.
When x is 1, y is exactly 1, is it? Or like,
No. When x is 1, it approaches infinity, you can say, like this. And this will go like this. But we're only taking from 0 to 1.
is it like log 1 plus 1 by x? Oh no, log to infinity, but no.
Okay, fine. I'll just tell you for now. So this is minus log of one minus x. So your initial log function will look like, let me see. Wait. I do the empty side. Okay, I just don't want to do it. So your log function is like this, right? And I take minus log and I get this, right? And then I do minus x first. So that's going to flip this about your y-axis like this. And then I add 1 and that's going to give me this. Is that fine? Did you guys get it?
Yeah.
Okay, fine. So basically, this is what your cost function is going to look like. So you'll realize that we have two cost functions. For one is for y equal to 1, one for y equal to 0. So can you tell me how I can combine these two to just make one loss function? Because having two is going to be a little tedious, because you have to keep checking if y is equal to 1 or 0 and then applying a different cost function. So is there any way I can combine these two and just make it one? Do you guys have any idea how to do that?
Maybe you could make something like 1 times the value of not y minus minus of minus 1 to the power of in this case of y into h theta of x. So depending on the value of y, it will create the function.
Okay. Your idea is right. Maybe try not using anything with powers in them, something simpler.
I got it. It's y into the first term plus y minus 1 into the second term.
Yeah, okay, fine. Yeah, that's perfect. So you'll get it something like this, right? So if you see here, when y is equal to 1, then your second term over here becomes 0, and you're only left with this term, which is what we want. And when y is equal to 0, your first term becomes 0, and you're left with the second term, that is minus log of 1 minus x. So it's good, mathematically speaking, it's going to look like this. Did you guys get it? Any doubts?
Hello.
Yeah.
Wait, it's me. So guys, are you following through so far? Because a lot of you have been silent for this session.
Yep, it's cool.
So in case you guys are having trouble finding out, what's going on, go through linear regression, because as I had said, and as you guys can also see, logistic regression is basically built on top of linear regression. So if you have any questions, feel free to ask us. He has been answering all your queries. I'm also there in the chat in case you need, don't want to ask it in front of everyone. But yeah, if you have any queries, do feel free to ask, because as stated earlier as well, logistic regression and the sigmoid function itself will be used in deep learning as well. So everything you learned in machine learning is also used in deep learning. So you can't really, skip to the good part. So yeah, that's that.
Yeah. So any doubts, please? So I can continue, right? Okay, fine. I'll just take that as yes, and we'll move on. So, remember again, the same as linear regression. You have a loss function over here, and to perform gradient descent, you'll have to differentiate it partially with respect to each parameter. So I'm not going to do the differentiation because it's a little too lengthy, but you guys should try it out once you go after this session, because it's a good exercise. Right. So again, your simultaneous parameter updates happen as usual for linear regression, and you'd notice maybe that your derivative is the same as it was for linear regression. So once you try it out, you can always verify that it should come the same as what you got for linear regression. So any doubts in this slide, guys?
No?
Okay. Just give me 2 minutes. Okay, so that was logistic regression. So I'll just stop here and I'll ask you, do you guys have any doubts in logistic regression? Like whatever has been explained so far? Any doubts? Okay, fine. I'll take that as a no, and then I'll continue probably. So, so now that we've learned 2 machine learning algorithms, I think it's best to understand machine learning and how it's structured. So you have 3 main categories for machine learning. There is supervised, unsupervised, and reinforcement. So supervised under supervised you have regression and classification. So you guys can go through these slides later on. We have different applications for each type. Basically, supervised learning is where you're giving the model the data beforehand. So suppose in the case of your house price prediction, you're giving the prices of each house beforehand to the model. So that will come under supervised learning. And similarly for classification, as we just saw for logistic regression, you're giving whether the email is spam or not, right? and so that comes under supervised learning as well. So when you look at the other side, you have unsupervised learning. That's where you don't give your model any information of your data. In a sense, you don't give it any labels. So that's what K-means clustering will tackle, where you give it all these data points, but you don't exactly tell it what they are. And so it has to figure out certain patterns or techniques within the data set to predict certain things. Then you have dimensionality reduction. You'll be learning this, I think, in your 4th session under PCA. So that's basically used for, suppose if you have 100 features or something in your data set, and it's not really useful to use all 100, and your matrix multiplication and your computation becomes really expensive, because usually data sets come much more than 100 features. So dimensionality reduction will help you in reducing all those features and sort of like picking out the best features or the most relevant features. Then you have reinforcement learning. Basically, it's like where you have an agent and it's trying to play a game, and you're giving it certain rewards for certain actions. And like it's basically how you see OpenAI, and then how it's playing Atari games, or how the I think last year I think OpenAI was a Google Mind. They beat the champion in Go, right? So like that was all reinforcement learning. So that's something which we won't be doing in these sessions, but you should definitely look it up. So yeah, coming to differences again, as I explained, supervised learning.
I have a question.
Yeah, tell me.
Previously, you said that in supervised learning, in the logistic regression, we give the model whether the mail is a spam or not a spam. But isn't the model supposed to tell us if it's a spam or not a spam? Like, what does the model do?
So when you're training the model, that's when you're applying your gradient descent, right? The loss function over here. This is where y is your spam or not spam, 0 or 1. You're going to apply this parameter updates, this third line over here. So let's say if you have, let's say we train it for like 10 epochs or something, right? So we're going to apply this for loop for 10 times, and you're going to get your set of parameter values. That is for your training set. Your training set is basically the data which you have already with you, and then you have another set called your test set. So basically your test set is data which your model has never seen before. So let's say that we have 10 emails. Let's say we have like 500 emails, suppose. And typically what happens is you will have 80% of them given to your training set and 20% as your test set. So 80% of those 500 emails is what is going to be used in your training over here, where you're setting your parameters and differentiating and applying gradient descent. After you train for 10 epochs, you're going to have a set of theta values. Those theta values are what you're going to use for your other 20% of your test set. So the equation which I think, where was it? Over here, right? So this is what you'll use for your hypothesis. So you're going to have thetas already learned by you after your 10 epochs or so. And x is basically your test set. So once you apply your sigmoid function and you multiply all of them together, you're going to get a hypothesis. That's either 0 or 1. And that's where your predictions happen. Does that make sense?
Yep, got it. Thanks.
Yeah. Okay.
Okay, so just to provide a little bit more clarity, so when you mean supervised learning, the word supervised means you are doing it under the supervision of something, right? So in this case, it's known as supervised because you're doing it in the presence of the right answers. And in this case, the right answers are your y values, for that matter. So talking about the house price prediction, you are initially providing the vector of y values, right? So in this case, you are providing the right values to the prices of the houses themselves. So those are known as the right answers. And what your model is doing is basically learning the parameters for the right values. So once it sees, let's say, any given set of parameters, area, number of rooms, so on, it can use the parameters it has learned to predict the price of a house it has not seen before. So these are the models that are used, in the real world. So you train it on, large amounts of data that you have, and you find the parameters, and then you kind of deploy your model. the model on wherever it has been deployed for that matter will get new features. Let's say some user wants 10 rooms in his house, and so that model will try to predict what would be the price of a house if there are 10 rooms. So that is the testing phase, because you're testing how well the model is doing. Training is the process where you're learning the parameters itself to create the model. So that is supervised, and unsupervised is basically you do not have the correct values. In this case, all you have is data about the houses. So in this case, assume that I give you the number of rooms that are present. I give you all the features about the house, but I don't give you the actual prices of the houses. And I tell you, okay, I have probably gone from door to door, and I've like made a data set of the various features of all the houses I've visited. I have no idea about what the price of the houses are. All you have to do is just do something with the data and tell me what you can find out. Now that is a case of unsupervised, because you don't know, like you're not giving it any kind of right answers. In fact, you're asking the machine to kind of give you some kind of clarity or give you some kind of interpretation from the data it has. That is a case of clustering. And dimension reduction is kind of self-explanatory. Let's say you have 100 features, you are trying to cut it down to 10 features, but the 10 features sort of need to be the most important features, right? Because you don't want to lose information. So in that case, use something known as dimension reduction, and there are multiple techniques for that. We'll be covering those later. So yeah, I hope this was clear for supervised and unsupervised. Yes or no would probably help.
Yeah, it
But
was. Thank you.
does that mean that
Yeah.
is much simpler than linear regression? Because it only has like 2 outputs, right?
I didn't get the first part of the question. Does that mean that?
1 second.
I think he asked if logistic is better than linear.
Oh, no. I was asking, does that mean that logistical regression is much easier, simpler than linear regression, because it only provides 2 possible outputs, right? Because it's binary classification.
There isn't a way you can compare, because one is used for regression, that is, linear regression is used to predict a continuous real value, whereas logistic regression is used for classification purposes. So they're used for 2 completely different things, right? So you can't really compare between the 2.
Oh, okay, cool.
If you're asking in terms of complexity wise, since logistic regression requires you to also perform linear regression until the sigmoid step, right? So you could say logistic regression has one extra step for computation purposes. If that's the question, that is.
Okay, thanks.
I had one question. So unsupervised learning would be not a good solution for the house price thing, right?
No, because the thing is, unsupervised is used to basically find patterns in your data. It's not used to create a model, because you cannot really deploy those kind of models. Unsupervised learning techniques are used for, they're used to aid other kind of applications. For example, clustering, as you can see, it's, what was written there. There's customer segmentation, there's targeting marketing, there's recommender systems. These are used to drive other various applications in ML. So yeah, unsupervised is generally not used entirely on its own. It is used to help something else. So you'll see that later, probably a bit later. To predict election results, do we not use unsupervised? No. You use past data, so don't worry about that. That's different. Unsupervised or clustering, whatever we'll be talking about now, is basically used to find similar groups of data or to find patterns in your data. For example, let's say you see that, for example, I'm just making an example here. So suppose you have the data about houses as that was present. Now supervised will just be able to tell you, for this set of features, the price of a house will be this much. But for another set of features, the price of a house would be something else. But unsupervised learning will tell you stuff like, okay, 60% of the houses are probably having 6 rooms, but the another 20% is having, let's say, 5 rooms, and so on. So these are type of patterns it can pick up. So unsupervised is powerful because it can pick up patterns like these. Targeted ads are unsupervised. They are, I mean, at one step, yes, it is. Because, okay, I'm just going to give you a surface level explanation of what happens. So let's say, you buy a certain set of items, okay? And another user buys a very similar set of items. Then in that case, what happens is the machine will be able to pick up the pattern that, you guys are sort of buying this most similar items. Whereas let's say there's another user C who buys completely different set of items. Then, the machine will also be able to tell that, okay, there's a large amount of distance between these two customers because they have a very different, shopping basket or whatever. So at a surface level, it works like that. It looks for patterns like these in your data.
Hey, I had a doubt too.
Yeah.
So could we say that supervised and unsupervised are like used for totally different purposes? Because supervised is basically for like expectancy and unsupervised is for like pattern detection types.
Yeah, correct. Supervised is basically when you have the right values. So you know the expected values and you are trying to match the expected values. Whereas unsupervised, you don't have any set of expected values. Because let's say I give you like the same data set of houses, right? Now a machine can easily pick up patterns in that data. But if you were to divide the houses based on number of rooms, you'd have to manually go through them slowly. Whereas a machine will be able to do it much faster.
All right, good.
No, Pranav says unsupervised is vague. No, it is not vague. In fact, unsupervised algorithms are simpler than your supervised algorithms. I don't know why you're calling it vague, but basically unsupervised works without any right answers. So unsupervised, in a way, also most importantly, unsupervised adjusts to your data. Okay, so what I mean by that is, for example, supervised, you have to give it the right answers to a house, right? And then you sort of give it a completely new house, and it has to predict the price for the new house. Whereas for unsupervised, there's never a condition where you might have very rarely in some applications, you might be given a new house and you have to predict the pattern in which it comes in. Unsupervised is mainly used to find patterns in already existing data. Anyway, so that is it for supervised and unsupervised. I hope you guys have understood. The most basic, line of difference is that in supervised, you provide the right answers, whereas in unsupervised, you don't provide the right answers. Okay, Shreyas, I think you can move on.
Yeah, okay. So one type of unsupervised learning algorithm is clustering. So basically what this deals with is to group similar data points together. So like the example of say e-commerce where certain two customers are buying similar items, you might want to cluster them into similar groups and recommend them the same type of items. So there's one application where you can see clustering being used. So the math for clustering is a little involved, so I won't be going too much into it, but giving you a sort of explanation and intuition behind how it works. So K-means clustering. So basically K refers to how many clusters you want, or K-means. So let's say that in this data here, you have, it's easily seen that we have 3 clusters, but let's say we assume K to be equal to 3 and we apply the algorithm. You're going to have 3 clusters or 3 medians. So those 3 black dots you see there will be your 3 medians, and they'll be like the center of each cluster. So the main objective of K-means clustering is basically to minimize or to keep all the clusters together to the median, if that makes sense. So for a particular cluster, you want to make sure that all the points belonging to that cluster are as close as possible to the median. So that's basically what K-means clustering is doing. So let's take an example of, so let's say we're given this data set and we select K to be 2 in this case. So the first iteration, or rather the first step in your iteration, would be to select any K random points from your data itself. So we have 2 centroids or medians, C1 and C2, and they're basically any 2 random points in your data itself. You don't want it to be any random points in your distribution or your graph, but you want them to be any two random points in your data range. Next, what you do is you will assign all the points closest to each cluster. So basically, if you take C2, and let's take a random point over here, this point here. Let's just say. So let's take this point, and you'll measure the distance of this point to the first median and to the second median, and you'll compute which one is closer. And since it's closer to the green one, you're going to assign this to the green cluster. And this is going to be repeated for all your points until each one of them is accounted for. Right, so once you do that, you'll have it like this. It's going to look something like this. And step 4 is where you recompute the centroids of newly formed clusters. So what that means is, let's say that your original centroid was over here, and after applying assigning each point to a cluster, you're going to find the center of the cluster itself. So let's say that if these are my points, these green points, you're going to want to find the center of all these green points. That's basically where you want your centroid to be. So if you take with respect to a graph, you would add all the x values and then divide by n, and all the y values and divide by n, and you'll get one x comma y coordinate, right? So that's going to be where you're going to put your green centroid at, and this is what you're going to repeat for each and every cluster that you have. So that's what we compute the centroids of newly formed clusters. And so then once you have your centroids done, you're going to repeat this process again. So basically, let's say that if you take this point over here, it might be closer to your green centroid than it is to your red one. So then you're going to reassign this back to green, then red. So you're going to keep repeating these steps over and over. Usually, one way of stopping your iterations is either you mention a number of epochs. So you said, maybe you might say, I'll stop this algorithm after 20 epochs. So after recomputing your clusters 20 times, you'll stop, and whatever clusters you have over here, you're going to assume that is to be your final clusters. Another way of doing it is you're going to measure how far each centroid is from its previous iteration. So what we're going to do is, if the difference between each centroid and its previous one is under a certain threshold, you're going to stop the iterations over there. Right? So that's what, when to stop. So when basically the centroids are not changing anymore, or like a very minimal difference in their coordinates, so that's when you want to do it. Or you have a maximum number of iterations reached. So you usually specify a certain number of epochs beforehand, after which you would stop your algorithm. So I'll show you, I think there was one simulation for KMeans clustering. So you guys can go to this link, I'll put it on the chat once. Basically, let's take, so let's say this is our data, right? So we have 3 clusters, and we'll add a centroid. So I'm going to pick a random centroid in one of your data points. I'll add another one, another one. So you have 3 centroids right now. So first, what it's going to do is going to classify each point into the closest centroid. So this is what happens here. It's assigning each point to a centroid. After that, we update the centroids. So basically move the centroid to the center of the cluster which was assigned before. And then we reassign the points again, like this. And we update the centroids again. So this thing keeps happening until your centroids are almost not moving at all, or you reach a maximum number of iterations. Now what happens is, this can work if you have a really good value of k. So suppose a distribution like this, let's have 2 points, and we apply the algorithm. It's going to do something else. So basically, while applying clustering algorithms, it's very important that you know your data well. So it's always recommended that you plot or visualize your data set beforehand, and that's how you're going to know when or which algorithm to use in so that it best fits your data. So are there any questions so far?
Do none of you have any questions? Okay, what does adding the centroid signify? Okay, so so the one thing about K-means, okay, actually there are multiple things. I'll just talk about them quickly. So the first thing about K-means is you require the number of clusters you're trying to form. That is, you're trying to find the number of, that is, if you want it to like group it into sort of clusters, you need to specify a number K, which is the number of groups or clusters that you're trying to form. So in this case, K refers to the clusters, and with each cluster, there is also a centroid, if you have noticed. Shreyas, could you go back to the like proper distribution? Like a nice distribution, yeah. Gaussian mixture, yeah. So as you can see here, there are 3 groups, and he has added 3 clusters, rather 3 centroids, and just finish the entire process, no? Just, yeah. Yeah. So as you can see here, each cluster is also associated with a centroid, and that centroid kind of represents the cluster. So if you want, let's say, an average value for a cluster, it would be the value of that centroid. So yeah, so adding a centroid is basically, the first step where you kind of assign random values, or rather you take random points and you choose a centroid value. So that's the first thing, because you need to like know how many clusters you want. There are multiple methods to actually visualize your data. That actually comes in dimension reduction, where you will see how that is done. The second thing about K-means is there's a lot of it depends upon the, where you actually assign the first centroids. Because if you remember, the first step in the algorithm is to assign a random set of centroids. So Shreyas, could you like assign random places? Actually, in this case, it will work. Probably choose something else. Okay, DB scan. Okay. So just if you take 2-3 random places right now, okay. Yeah, so just run it a few times. Yeah, so you get this. So, okay, restart it and now add some other centroids. Like, don't add them in the same place. So, okay, in this case, it has approximately come to the same area, but it's not entirely the same thing. But a lot of it depends on the, the type of points you're choosing, or rather the selections that you're choosing. I think you might get a better representation of what I'm talking about here. But in this case also it will work, because most of the points are kind of randomly scattered. Anyway, so a lot of it depends upon the, the points that you decide in the beginning of where you assign the random points. Because if they are closer to the actual cluster centers, then obviously you'll take lesser epochs. But if they are far away from them, you will also take more epochs. So also sometimes when you have, let's say, this is a nice distribution, so you're gonna get, like a nice cluster centroid and stuff. But sometimes based on the distribution, you might not even converge. So K-means has a problem where you might not get the cluster centers at all. That's the second thing. So yeah, K-means has these 2 major issues, which is you first need to know the number of centroids, and secondly, you might get a different distribution based on where your initial centroids are. There's also another thing where basically, as you can see in I think the density-based examples, it does not cluster very well. Where you have, something like this, yes. So you could argue that there are 3 clusters here, one on the left, one in the middle, and one on the right, based on density of the points. But K-means will not be able to figure that out, as you can see. It's not really forming a very good type of split, in a way you could say. There are other algorithms which can actually solve this, and there are other clustering algorithms which do not require a initial starter K value. That is, they can find out the number of clusters on their own. So yeah, that is K-means. Do you guys have any doubts about how K-means is actually performed? any practical application where K-means is preferred. The thing with clustering algorithms is it all depends upon the data you have. If you have data which can use K-means, you would probably use K-means because it is actually a very fast algorithm. Okay, it's not a fast algorithm. Okay, it works, or rather, it like as your data size increases, K-means also gets more computationally expensive. But the thing about K-means is simpler to work. It's simpler compared to the other methods.
Is there a use case scenario where you don't know the value of K, but you still use K-means clustering?
So as Shreya said, you first visualize your data and then you try to pick your value of K. If you cannot visualize your data, there are methods where you can pick the right K value. I don't know, Shreyas will be covering that now or later.
I don't think I'm doing it.
Do you have the K elbow method with you now?
No slides are linked. I thought.
Okay, it's fine.
Yeah.
Okay, I'll just talk about it. So, okay, so I'll talk about it towards the end. So yeah, you need to first visualize your data before actually choosing your clustering algorithm. Because as I said, K-means requires the number of centroids, but there's another algorithm known as dbScan, which does not require the number of centroids. So yeah, but if you do have the number of centroids, K-means should obviously be your first choice because it also works well. Okay, so, someone is asking if the centroids are the centroids towards the end random points on the graph, or do they have to be one of the data points themselves? It can be anything. You can either make up random points as your centroids, or you can choose points from whatever is existing in your data set. It does not really matter. Because at the end of the day, your centroids will shift, right? It's very unlikely that the first set of points you choose are the centroids themselves. The probability of that happening is, I think, K factorial by K power K. You kind of have this derivation in third year. So it's very low probability that is going to happen, so don't worry about that. Okay, so talking about how you exactly choose K. So the first and the easiest method is to visualize your graph. But there's something else known as the K elbow method. Just see if there's some kind of visualization for that. So I'll just talk about it until then. So what is the K elbow method? So basically, as you guys know, there is a set of loss, or rather a cost, which is there for K-means. The cost for K-means is basically the distance between each point in a cluster and the cluster centroid. It might be a bit difficult to understand without an equation on the screen, but you basically take every centroid and you take the distance of every point in the centroid you take every cluster, you take every cluster and you take every point and you take the distance of every point in the cluster with the centroid of that cluster. So you kind of, take the distance and you do this for all clusters and just add up the entire thing. So that is your cost. Okay. So once you have that cost, what you do is you basically perform K-means with a particular set value of K. Let's say K equals 1. Actually, K equals 1 doesn't make sense. So K equals 2. So you start with K equals 2 and you find the cost and you plot it on a chart. Then you increase the K value to 3, find the cost and plot it on a chart. You find the cost with respect to K equals 4 and so on. So basically you keep increasing the value of K until, let's say, 7 or 8, because that is usually a value people stop at. So you keep increasing the value of K and you also keep finding the cost with respect to each particular K value that you have. So now what do? Do you choose the value for which K is the least? Sorry, for which the loss is the least. What do you think will happen if I choose that value of K for which the loss is the least?
The loss and the cost should be the least, right?
Okay, I'm using the terms interchangeably, but I'm referring to loss as the entire loss of the entire operation. So that is the cost over the entire thing.
That centroid will have the biggest cluster.
No, I'm increasing the value of K and I'm also finding the cost for each value of K. So what do you think will be the value of k for which loss will be the least?
The more the number of centroids you have, the lesser the losses will be, right? Because the distance will be lesser because you have more clusters.
Technically, if k is equal to the total number of points in my data set, for that the cost will be the least. Yes. So, but that is not a good clustering, right? Because in that case, you're saying every customer is their own group. So that's not a very good clustering. Instead, what you do is, oh, my man found a direct blog article. Okay. So in this case, what you actually do is you want the cost to decrease to a nice low value, but at the same time, you don't want to overfit it. That is, you do not want the clusters to become smaller and smaller and smaller. At the same time, you don't want the loss to be very high. So there is a very popular method known as the elbow method, and this is the elbow method. So as you can see, there's a value of k, and I think epsilon here refers to the cost. I'm going to assume that here. So over here, they have plotted the value of k with respect to all the costs for each k value. And if you notice, there is an elbow in the curve, or rather sharp bend in the curve. Where do you think is the sharp bend in the curve?
That's like the ideal point.
Yeah, that is your ideal point of k, because that is the point where your cost has firstly completely sort of come down to almost your minima, but at the same time you have not like kind of gone overkill and made everything a new cluster. So that is your most ideal point to choose k. So this is the k elbow method.
So now this looks like a sharp, turn, like sharp curve, because you're plotting points at specific numbers, 1, 2, 3 integer values.
Yes.
If you start putting fractional values, it will probably become more.
You can't have fractional values, right? What's 2.5?
Yeah, right. But if you do that in this function, you'll probably get start resembling regular curves, right?
Well, in a way, yes, but you can't really have that, right?
Yeah, correct.
You don't have something called 2.5 clusters.
I know, yeah. Got it.
So yeah, in most cases, however, you will not get a very nice looking elbow like that. You will kind of get something like this. It's not, a very nice looking elbow, but you usually get some kind of curve. In this case, as you can see, the elbow is around 3. 3, 4, whatever you want to use, around that point. Okay, one second. Let me just look at the questions. I thought by loss you meant the distance from the points that haven't been grouped in the right category. Okay, so there is no definition of right category here, because as I said, there are no right answers. It's whatever the machine gets at that point. So everything is kind of considered right. So the cost is basically, or the loss, let's say, for every cluster, you find the distance of the point in that cluster to the centroid itself. So let's say there are two clusters and cluster 1 has 5 points. For cluster 1, you find the distance of the 5 points with the center, and in cluster 2, let's say you have 6 points, you find the distance of the 6 points with the centroid of the second cluster, and then you just add up the distances from both, whatever you get. So that is your loss. Okay, at the ideal point, can we say the groups are equally size distributed? No, that is not the thing. At the ideal point, you do not want equal size things, okay? Because in most cases, your clusters are not equally sized, right? So at the ideal point, what happens is the distance between a centroid and the other points in the same cluster are the lowest. It is not that you have equally sized stuff. Okay, what is K? K is the number of clusters. Why is there such a sharp change? Okay, usually will not get a sharp change like that. Okay, that's kind of like one-off case, but in most cases, like Shreya showed the other one, that is when you will get you usually get a curve. You don't really get an elbow bend like that. You usually get kind of like a curve with a higher curvature at that point. So the reason that happens is because as K increases, your loss will also come down, right? But what happens is at one particular value of K, or rather, as your k increases in the beginning, it will start coming down very quickly. Okay, because you're slowly increasing the value of k and it starts decreasing. But after a point, what happens is, if you have noticed the visualization that was there, you have seen that towards the end, the centroids stop moving by much, right? They just move a little bit here, a little bit there, just adjusting themselves, not really completely moving across the entire graph. So that is when you have hit that particular area. Okay, so if you had to compare it with the steps in the visualization, the bend comes at the point where the centroids stop moving too much. And of course, as you increase the value of k, you're sort of approaching the point where the centroids stop moving completely. So that k equals that is a point where you have sort of the lowest amount of loss without having too many types of, having too many, clusters. What is epsilon? Okay, epsilon in this case is
the wrong graph. It's the graph of epsilon versus iteration number. The k value is fixed for this one.
Yeah, I mean, it's k value versus something else is usually loss. I don't know what epsilon here refers to.
So I was saying, so like suppose this was the graph, what would be the ideal value of k here?
High curvature, so around 3.
Okay, so what is it? Do we find the graph or slope of this and find the lowest value in that?
Yeah, so that is a bit overkill. People generally just look at the graph and just pick whatever works.
I mean, it's okay, cool.
I mean, because you can visualize your data and see, right? I mean, you will be using that if you're doing KMeans. You will be visualizing your data. So
you said only 7 to 8 is the max to go to, right?
Yeah, I mean, you don't tend to have more than that, because you're kind of overfitting at that point if you have more than 10 clusters.
Okay.
Usually number of clusters won't really differ by that much unless of course your data is in that way. Like if you actually have that many groups, you will have that many, but usually not really. You don't really get that many. See, in some cases it's easy to identify number of clusters. For example, the Gaussian distribution in the earlier one, you could see that there are 3, but in some cases like this one, you don't really know. What smiley face? Oh wow, do for this. Yeah, so as you can see here, you'd probably want the eyes and the mouth to be a cluster. That is their own clusters, and the face or the ring of the face a completely different cluster. Okay, so how is overfitting bad? We will be talking about overfitting and underfitting later, probably some other session. But just to give you an example, to give you a rough idea, overfitting is basically when your model starts memorizing and not learning. To basically tell you how that means, let's say you're studying for a test, okay, and instead of learning the chapter, the topic, what you do is you basically mug up the last 10 years questions and you go. So now what might happen is, if there's a question from the last 10 years, you will do well, okay. But if there's a completely new question which you have never seen before, you are going to fail in that question, okay. But on the other hand, if you had learned the topics and gone, you would have probably done, decently or kind of well in all the questions that came. Why? Because you learned the topic and you didn't memorize the questions. So that is kind of the thing. And underfitting is the opposite, where you don't study and go. It's like a very surface level explanation of what that means, but that is actually kind of the best example I can give you at this point.
So like I thought the smiley face wouldn't give the eyes and the mouth distribution all the time, so I tried it, and yeah, so like sometimes it gives you both the eyes in one and half the mouth in two others.
No, I'll tell you. So the point is not to get like that. The point is to the point of a cluster is basically the distance between the centroid and all the other points have to be minimum, right? So Shreyas, could you open the thing again?
No, I got that. So I was just asking, like, the what is the use of K-means clustering? Like, is it like some specific use scenarios?
Yeah. So okay. So assume the various points in the smiley face here are customers. Okay, trying to buy something. Okay, and you could say that the eye on the left is our customers who buy, let's say, sports equipment. Okay, the eye on the right are customers who buy uh, probably something else, electronics. Okay, and you could probably say that the mouth has some other category and the face also has some other category. So if you're given such points, you need to figure out the, what do I say, the clusters, right? You need to find the groups of data. So in that case, K-means clustering will give you these groups. It will tell you that given a point in your data set, which category or what type of items that person will buy.
Okay, cool.
So yeah,
You can do a DB scan on the smiley face to get like different shapes. Like the outline is different and the eyes and the mouth is.
Wait, is DB scan there on the visualization? Just for the one can do.
Yeah,
Put the link on the. Okay.
Yeah. So I'm not going to talk more about DB scan, but DB scan is one of the higher end clustering algorithms that exist. It's a very recent algorithm, actually. It's like around 2000s, I think it came out. So DB scan, the way it clusters is it does not look at the distance, unlike K-means. In fact, it looks at the density. So the assumption it makes here is points that are together are part of the same cluster. Points which are not together are part of different clusters. So that is why in the case of the smiley face, DB scan would actually do a much better job, or at least I'm hoping so. So yeah, don't worry about the parameters for now for DB scan. So as you can see, all the points that are close to each other sort of get clustered on their own. Okay, probably you need to increase the epsilon value, right? Okay, it's still working, so overwriting. So. So as you guys can see, every single sort of dense area was made its own cluster here. So this is DB scan. As you can see, it's way more powerful than K-means. It's able to identify very good clusters here. So we're not going to go into details of how this works. If you're interested, feel free to look it up. DB scan is actually not that complicated to understand. It's also got a more or less simpler way how it works, similar to K-means, but the algorithm is a bit more complex to actually do. But it's all simple math. It's not too complicated. So it looks at the number of points in a certain area. Okay. Any questions about anything else? Shreyas, you can take over if you have anything else to talk about.
I think I'm done with my session.
Okay, I guess that's it for the ML session. You guys can, leave your feedback or ask your questions now. You guys have any questions?